In October 2002, the mechanical era of the American highway came to a close. The Cummins N14, the most trusted diesel block on the interstate, was officially discontinued. Forced out by new EPA emission standards stemming from a late 1990s consent decree, the raw iron and fuel that built American trucking gave way to the era of exhaust gas recirculation, or EGR. Independent owner-operators did not just lose an engine line. They lost a machine they could rebuild in a truck stop parking lot. They traded a million-mile mechanical rhythm for flashing check engine lights, sensor failures, and mandatory software diagnostics. The paradox is that the N14 did not die because it failed. A decade earlier, that exact sound had meant absolute American industrial strength. The engine had not lost its pulling power. It had simply become illegal to build. But the real story of the Cummins diesel is not just the story of an emissions rule. It is the story of how an engine block taught American freight to trust a sound, and what happened when that sound became too expensive to keep. Every week we tell the stories of American engines, factories, machines, and industrial names that once taught the country what power sounded like, and what happened when the market moved on. Subscribe if that history matters to you. The story begins not with nostalgia, but with a specific place, in Columbus, Indiana, in 1919. In 1919, the American highway system barely existed. Freight moved by rail, and local deliveries moved by horse or early gasoline-powered trucks. In Columbus, Indiana, a mechanic named Cummins Cummins convinced a wealthy local banker, William G. Irwin, to fund a company dedicated to building oil-burning engines. For the first decade, Cummins Engine Company was not a highway legend. It was a financial failure. The factory floor in Columbus produced small, single-cylinder stationary engines used on farms and in marine applications, built under license. They were temperamental, they leaked, and they did not make Irwin any profit. To understand why the early Cummins Company struggled, you have to look at how America understood power. At the time, if a machine moved, it was usually powered by steam or a gasoline engine. A gasoline engine, a power plant that relies on a spark plug to ignite a highly volatile mixture of air and fuel, was relatively light and easy to start, but it was thirsty, and under the heavy grinding load of a commercial truck, its ignition system was prone to failure. The alternative was the diesel engine. A diesel engine, a machine that draws in only air, compresses it until it becomes superheated, and then injects heavy fuel so it ignites purely from the heat of compression, was incredibly efficient. It produced massive pulling power and ran on cheap, low-grade oil. But in the 1920s, a diesel engine was an enormous, static piece of iron. It weighed thousands of pounds. It was bolted to the concrete floors of power plants or set deep into the bellies of ships. It ran at a fixed, slow speed. It was entirely unsuited for the changing RPMs, the jarring vibrations, and the physical constraints of an American truck chassis. Cummins realized that if his company was going to survive, the diesel engine had to move. It had to become lighter, spin faster, and throttle up and down predictably like a gasoline engine. The engineering hurdle was the fuel system. Early diesels used cumbersome air injection systems to blast fuel into the cylinders. Cummins developed a mechanical system that metered and pressurized the fuel using a single distributor pump, allowing the engine to respond to a throttle pedal. By the late 1920s, the company was nearly bankrupt, and Irwin was ready to pull his funding. Cummins needed a stunt to prove that a diesel block could survive the American road. In 1931, he installed a prototype Cummins Model U diesel into a heavy-duty Marion truck. He and a co-driver departed from New York City, aiming for Los Angeles. It was not a race for speed. It was a physical argument about efficiency and endurance. The truck arrived in California 97 hours later. The total fuel bill for crossing the entire United States was $11.22. That number, $11.22, was a shock to the American freight industry. It proved that the fuel economy of a diesel could completely rewrite the operating costs of moving goods. But a publicity stunt does not build a company. An engine must survive where Americans buy, service, and depend on machines. The true American market entry happened a year later in 1932 in the mountains of California. Purity Stores, a regional grocery chain, operated a fleet of trucks that had to haul heavy food supplies over the punishing grades of the San Joaquin Valley and the Sierra Nevada foothills. Their gasoline trucks were burning tremendous amounts of fuel and constantly suffering from overheated engines and burned valves. Cummins offered them the new Model H. The Model H was a 672 cubic inch inline six. It was an engine with 6 cylinders arranged in a straight line, designed with the exact physical dimensions needed to slide into the engine bay of an existing commercial truck. Purity stores took a chance and ordered the diesel engines for their Mack truck fleet. The results shifted the gravity of the trucking world. On the mountain grades, the Cummins Model H did not stall, it did not overheat, and it cut fuel consumption dramatically. The drivers realized they no longer had to constantly shift gears to keep the engine from dying. They could simply lean on the diesel's low-end pulling power. Purity stores became the first major American truck fleet to adopt diesel power, proving that the high initial cost of a diesel block was easily erased by the fuel savings and durability on the road. This early adoption by California fleets set the stage for the architecture that would define Cummins for the rest of the century. As the 1930s bled into the 1940s, the demand for highway freight began to swell. Truck manufacturers like Kenworth and Peterbilt began offering the Cummins Model H as factory equipment. The block, the massive cast iron foundation that holds the cylinders and the rotating internal parts, was overbuilt, designed with thick cylinder walls and heavy main bearings that could be overhauled and rebuilt indefinitely. In the years during and immediately after World War II, Cummins engineers took the fundamental architecture of the Model H and expanded its bore and stroke. They increased the displacement. Displacement, the total volume swept by the pistons inside the cylinders, which dictates how much air and fuel the machine can process, was pushed to 855 cubic inches. This new series, known as the NH, would become the bedrock of the American highway. The 855 cubic inch block was a massive, naturally aspirated inline six that delivered a kind of mechanical trust the country had never seen. It was simple, it was heavy, and it could be repaired with basic hand tools in a dirt lot if necessary. It turned Columbus, Indiana, into one of the most important manufacturing centers in the Midwest, a factory town where foundries poured iron and machining lines cut steel to keep up with the demands of a growing nation. By the late 1940s, the blueprint was set. The engine had proven it could survive the road. Now it had to prove it could build an empire. The true breakthrough for Cummins did not happen on a single day. It happened because the American map was being completely redrawn. In 1956, the Federal Aid Highway Act authorized the construction of the Interstate highway system. This was not just a paving project, it was a fundamental shift in how the country did business. Before the interstates, heavy freight moved primarily by train. Trucks were largely used for regional delivery, navigating winding, two-lane state routes where speeds were low and trips took days. The new interstate system meant a truck could run at 60 miles per hour for hours on end, crossing state lines without stopping for a traffic light. This new geography created a brutal mechanical problem. Fleet operators like Consolidated Freightways and Roadway Express needed trucks that could haul maximum legal weight across the country at sustained high speeds. A gasoline engine running at wide-open throttle for 10 hours straight would eventually overheat, burn its valves, or suffer catastrophic ignition failure. Early diesels were durable, but they were often sluggish and produced heavy black smoke that choked out following traffic. The fleets needed a power plant that could deliver massive pulling power, survive continuous highway speeds, and keep fuel costs low enough to make the freight math work. Cummins answered with the continued evolution of the 855 cubic inch block, but the true engineering breakthrough that locked in American fleet trust was the fuel system. While other manufacturers were experimenting with complex, sensitive distributor pumps, Cummins perfected the PT fuel system. The PT, or pressure time fuel injection system, a uniquely mechanical design that uses a simple low-pressure gear pump to move fuel to the injectors, while relying on the engine's own camshaft to mechanically slam a plunger down and create the extreme high pressure needed for injection, changed the reality of truck maintenance. In an American fleet maintenance shop, the PT system was a revelation. It meant a mechanic did not need to calibrate a fragile, expensive high-pressure pump on a specialized dust-free test bench. The system was robust, simple, and entirely mechanical. It was just gears, plungers, and fuel. If a truck was pulling a heavy load through the deserts of Arizona or the freezing winds of Wyoming, the PT system ensured the engine would keep firing steadily as long as it had clean fuel and air. But as the trailers got longer and the loads got heavier, naturally aspirated engines began to run out of breath, especially at high altitudes in the Rocky Mountains. Cummins solved this by fully embracing forced induction. They added a turbocharger. A turbocharger, a device driven by hot exhaust gases that spins a compressor wheel to force more dense air into the engine, allowed the 855 block to burn more fuel and generate massive power without increasing the physical size of the iron casting. This birthed the legendary NTC series of the 855, including engines like the NTC 335 and the NTC 350. When a driver in a Kenworth W900 or a Peterbilt 359 downshifted to climb the Donner Pass, the turbocharger would spool up, emitting a distinct, high-pitched whistle that became the signature soundtrack of American trucking. The forced air translated directly into torque. Torque, the twisting force of the crankshaft, often felt as the sheer physical pulling strength of an engine, is what actually moves an 80,000-pound combination up a 6% mountain grade. Horsepower, a measurement of how quickly an engine can do work, dictated the top speed on the flatlands, but torque was what kept the freight from rolling backward. The mechanical brilliance of the Cummins 855 was not just in how it ran, but in how it was repaired. The engine was designed with wet sleeves, removable, replaceable cylinder liners that sit in direct contact with the engine coolant, meant that the massive cast iron block was essentially immortal. When a conventional engine wore out its cylinder walls, the entire block had to be pulled out of the truck, sent to a machine shop, bored out, and fitted with oversized pistons. It was an expensive, time-consuming process that kept a truck off the revenue-generating road. With a Cummins wet sleeve block, a mechanic in a regional truck stop in Ohio or a fleet garage in Texas could simply drain the coolant, pull the cylinder head, yank out the worn steel sleeves, and drop in brand new ones along with new pistons and rings. In a matter of days, the truck had a completely rebuilt internal engine, perfectly within factory specifications, without the heavy iron block ever leaving the chassis. This rebuildability completely changed the financial calculations of American truck fleets. The initial purchase price of the engine was an investment, but the total cost of ownership over 1 million miles was untouchable. By the 1970s and 1980s, this combination of the PT fuel system, reliable turbocharging, and wet sleeve rebuildability turned Cummins into a monopoly of trust. Depending on the year and the specific market segment, over half of all heavy-duty Class 8 highway trucks sold in the United States were ordered with a Cummins diesel. Truck manufacturers like Freightliner, Kenworth, and Peterbilt built the trucks, but the fleets specifically requested the power underneath. The engine had bridged the gap from a risky alternative fuel experiment to the absolute standard of American freight. Drivers learned to tune the overhead valves by ear. Mechanics memorized the firing order. Fleet owners built their profit margins around the fuel economy. Cummins was no longer just an engine builder. In the American truck stop, the red paint on the block had become a currency of trust. By the late 1980s and into the 1990s, the Cummins 855 cubic inch architecture had evolved into its masterpiece, the N14. In an America where an engine could decide whether a field was cut, a truck made its delivery, a boat left the dock, a generator carried a hospital through a storm, or a plane lifted from the runway, power was not an abstraction. It was iron, fuel, labor, heat, sound, repair, and trust. The N14 was the physical embodiment of that trust. It was still the massive inline-6 wet sleeve block that American fleets had relied on for decades, but it had been refined to a point of mechanical near perfection. Cummins introduced articulated pistons. An articulated piston, a two-piece design using a forged steel crown to withstand immense combustion pressure and heat, pinned to an aluminum skirt to keep the moving mass light, allowed the engine to survive extreme internal forces. They upgraded the cooling system and optimized the cylinder heads to let the engine breathe freely under heavy loads. The result was a machine that fundamentally changed the expectations of an American fleet. A well-maintained N14 regularly achieved a million-mile overhaul interval. A million miles, roughly equivalent to driving around the Earth 40 times, before the cast iron block needed to be opened, the sleeves pulled, and the internal components replaced. In the parking lot of the Iowa 80 truck stop, or in a dirt pull-off on Interstate 40 in Texas, the sound of a fleet of N14s idling at 600 RPM was the baseline frequency of American commerce. Independent owner-operators, drivers who owned their trucks and absorbed every single maintenance cost personally, specifically ordered the N14 in their Kenworth W900s and Peterbilt 379s. They chose it because it offered a predictable financial equation. The N14 Select Plus variant could be tuned to push out a verified 525 horsepower and a massive 1,350 pound-feet of torque. It could drag an 80,000-pound load over the Rocky Mountains without the coolant temperature ever spiking into the danger zone. To keep up with rising fuel costs and the very first waves of mild emission standards in the early 1990s, Cummins introduced the Select system. Select, an electronic fuel injection system that used a computer module, or ECM, to precisely time the firing of the injectors instead of relying entirely on mechanical throttle linkages, was an early bridge between the physical and digital worlds. It gave fleets better fuel mileage, provided drivers with smoother cruise control, and allowed mechanics to read basic diagnostic codes. But crucially, the underlying hardware remained the same heavy-duty, rebuildable iron block. The mechanic in a Nebraska repair shop still recognized the machine. If a sensor failed, the engine could usually still limp to a service bay. The electronics were layered on top of the iron, but they had not yet taken absolute control of it. During this era, Cummins dominated the American industrial landscape. In Columbus, Indiana, the factory lines ran relentlessly. Local foundries poured thousands of tons of raw iron. Machine shops cut exact tolerances into the blocks. The service network, a sprawling, nationwide web of authorized dealers, fleet mechanics, parts counters, and independent repair shops, spoke the language of Cummins' part numbers like a native tongue. But highway freight, as massive as it was only one side of the empire. To truly achieve absolute scale, Cummins was about to take their heavy-duty diesel philosophy, shrink it down, and park it directly inside the American garage. While the N14 was dominating the heavy-duty freight lanes, Cummins made a move that altered American garage culture forever. By the late 1980s, the American consumer pickup truck market was dominated by massive gasoline V8 engines. The diesel options available from Ford and General Motors were generally seen as sluggish, underpowered, and primarily intended for light fuel savings rather than brute strength. In 1989, Dodge made a desperate play to revive its failing Ram pickup line. They formed a partnership to drop a commercial-grade Cummins engine directly into a 3/4-ton consumer truck. The engine they chose was the 5.9-liter 12-valve Cummins. The 5.9L was not a car engine scaled up. It was a tractor engine scaled down. It was a heavy-cast inline-six originally designed for case agricultural tractors and medium-duty delivery box trucks. The term 12-valve referred to the cylinder head design, two massive valves per cylinder operated by a simple heavy-duty pushrod system. But the true magic of the engine, much like its bigger highway brothers, was its fuel system. It utilized a purely mechanical Bosch injection pump. A mechanical injection pump is essentially the beating heart of an older diesel, a gear-driven mechanism that forces high-pressure fuel to the injectors without a single computer chip, sensor, or line of code involved. When the 1989 Dodge Ram Cummins hit the American market, it was a revelation. It offered 400 pound-feet of commercial-grade torque in a truck that could be parked in a suburban driveway. For the American farmer pulling a heavy horse trailer or the independent contractor hauling a skid steer, the 12-valve Cummins was a miracle of physics. It did not overheat on steep grades. It got surprisingly good fuel economy. And most importantly, it was nearly indestructible. The 12-valve Cummins did not just sell Dodge trucks, it created an entire aftermarket culture. Mechanics and weekend wrenchers quickly realized that because the Bosch mechanical pump was controlled by physical springs and fuel plates, they could use basic hand tools to increase the fuel flow. An engine that rolled off the assembly line with 160 horsepower could be tuned in a home garage to produce double or triple that power without snapping the massive forged steel connecting rods inside the block. It brought the heavy-duty sound of an American truck stopped directly into the American driveway, complete with the black smoke and the heavy rattling idle that signaled pure mechanical compression. By the mid-1990s, Cummins had achieved an almost mythical status across the entire spectrum of American power. At the factory in Columbus, Indiana, the scale of production was staggering. Foundries were pouring iron around the clock. The assembly lines were shipping out thousands of red-painted heavy-duty blocks to Kenworth, Peterbilt, and Freightliner, while simultaneously sending hundreds of thousands of the smaller inline sixes to Dodge. The company had built an empire on a very specific promise, that an engine was a physical tool, and if you fed it clean oil and clean fuel, it would do the work you asked of it. A driver could diagnose a misfire by listening to the exhaust note. A mechanic could overhaul a block using physical service manuals stained with oil, measuring clearances with a set of feeler gauges. It was an ecosystem of total mechanical trust. In a perfect world, that mechanical simplicity would have run forever. But in the late 1990s, the American highway was about to inherit a new rulebook. The collapse of the mechanical American diesel did not begin with a catastrophic engine failure on the side of a highway. The first small crack appeared in a federal courtroom in Washington, D.C. in October 1998. For years, the major American diesel manufacturers, including Cummins, Caterpillar, Detroit Diesel, and Mack, had been engaged in a fierce war for fleet orders. The ultimate weapon in that war was fuel economy. Fleet managers calculated profit margins down to the tenth of a mile per gallon. To give the fleets what they demanded, engine builders had begun utilizing the early electronic control modules, like the Cummins Select system, to alter the engine's behavior based on driving conditions. When an American truck was operating on a flat, steady stretch of the interstate highway system, the engine's software would slightly advance the fuel injection timing. This made the engine run incredibly efficiently, burning less fuel and generating massive torque. But advancing the timing also caused the combustion temperatures inside the cylinders to spike, which produced high levels of nitrogen oxide, or NOx, a highly regulated pollutant. During the specific standardized laboratory testing required by the Environmental Protection Agency, the engines ran on a different, cleaner map. But on the open highway, they prioritized fuel economy. The EPA and the Department of Justice declared that this software programming constituted an illegal defeat device. The resulting legal settlement was one of the largest in industrial history. The manufacturers faced massive fines, with Cummins alone agreeing to an $83.4 million civil penalty. But the true consequence was not the fine, it was the timeline. As part of the consent decree, the heavy-duty engine manufacturers were forced to meet strict new NOx emission standards that were originally scheduled for 2004, pulling the deadline forward to October 1st, 2002. That specific date, October 1st, 2002, was the death warrant for the mechanical era of American trucking. The legendary N14 block, the engine that had powered 1 million miles of American freight without a major overhaul, could not be engineered to meet the new regulations in time. The basic physical architecture of the engine, its airflow, its cylinder head design, its cooling capacity, had reached the absolute limit of what raw iron could do against environmental law. After decades of dominating the truck stops, the N14 was officially discontinued. The mechanical simplicity that owner-operators had bet their livelihoods on was legislated out of existence. To survive the 2002 deadline, Cummins had to completely shift the American highway toward their new flagship engine platform, the ISX. The ISX was a highly advanced dual overhead cam engine, but to meet the new NOx requirements, it had to be equipped with a technology that fundamentally altered the relationship between a driver and their machine. Exhaust gas recirculation, or EGR, an emission system that routes a portion of the engine's hot spent exhaust gases back into the intake manifold to intentionally lower the combustion temperature and reduce nitrogen oxide emissions, was a massive engineering contradiction. For the entire history of the internal combustion engine, the goal of a diesel engineer was to feed the cylinders the coldest, cleanest, most oxygen-dense air possible. EGR did the exact opposite. It took hot, abrasive, soot-filled exhaust gas and forced it directly back into the breathing system of the engine. To prevent the engine from melting down, this exhaust gas had to be cooled before it re-entered the intake. This required an EGR cooler, a complex heat exchanger bolted to the side of the block, where boiling exhaust gas met engine coolant in a high-pressure environment. In an American fleet maintenance shop in 2003, the reality of this new system was a profound shock. The iron block of the ISX was incredibly strong, but the systems bolted to the outside of it were fragile. The EGR valves, the mechanical gates that controlled the flow of the exhaust gas, became sticky and jammed as they were constantly blasted with thick, oily soot. The EGR coolers, subjected to extreme, rapid temperature fluctuations as a truck pulled heavy loads up a mountain pass and then coasted down the other side, began to crack. When an EGR cooler cracked, it leaked liquid engine coolant directly into the cylinders, often leading to blown head gaskets or catastrophic hydrostatic lock. Drivers noticed that the engine oil, which used to stay relatively clean for thousands of miles in the old N14 days, now turned pitch black almost immediately after an oil change because of the heavy soot loads being forced past the piston rings. The engines ran significantly hotter, requiring massive redesigned radiators that changed the physical shape of American truck hoods. But the deepest crack in the foundation of fleet trust was the loss of control. In a dirt pull-off in Wyoming, an independent owner-operator could no longer diagnose a rough idle by listening to the mechanical clatter of the valves. If a sensor on the EGR system detected a parameter out of range, the engine's computer would trigger a check engine light and immediately put the truck into a D rate, a software-mandated reduction in engine power designed to protect the emissions equipment. A truck carrying 80,000 pounds of refrigerated produce could suddenly lose half its pulling power because a $2 electrical sensor failed in the rain. The repair manual was no longer enough. The mechanic needed a laptop, an expensive software subscription, and specialized diagnostic training. The iron was still highly capable of pulling the freight, but the engine was no longer just a machine. It had become a chemical processing plant, and the most painful lessons of the sensor era were only just beginning. If 2002 was the end of mechanical simplicity, 2007 was the beginning of an entirely new era of complexity. The Environmental Protection Agency introduced a new, drastically stricter set of emissions rules, forcing heavy-duty diesel engines to cut particulate matter, the physical black soot that characterized older diesels, by 90%. To meet this standard, Cummins and the rest of the industry had to introduce the diesel particulate filter, or DPF. A DPF is a massive honeycomb ceramic filter installed in the exhaust system that physically traps soot before it can leave the tailpipe. But an engine produces soot continuously. To prevent the filter from clogging entirely, the system must perform a regeneration. Regeneration is a process where raw diesel fuel is injected into the exhaust stream to raise the temperature inside the filter to over 1,000 degrees Fahrenheit, literally baking the trapped soot into ash. For the American truck driver, this changed the fundamental reality of operating a machine. If a truck was running a long, heavy grade in the Rocky Mountains, the exhaust was naturally hot enough to burn off the soot. But if that same truck was stuck in Chicago traffic or idling in a freezing warehouse lot in Minnesota, the filter would rapidly load with soot. The dashboard would light up. The driver would be forced to pull over, park the truck, and initiate a manual regeneration, sitting on the side of the highway for 45 minutes while the engine ran at a high, idle, burning fuel, just to clean its own exhaust pipe. Then came 2010, and another wave of federal regulations required a massive reduction in nitrogen oxides. Cummins was forced to bolt on yet another chemical processing plant, selective catalytic reduction, or SCR. This system required the use of DEF, or diesel exhaust fluid, a highly corrosive, urea-based liquid that is continuously injected into the exhaust stream to break down NOx into harmless nitrogen and water. Now, the American truck had two fuel tanks, a DEF tank, heated fluid lines, a dosing injector, a DPF, an EGR valve, an EGR cooler, and dozens of fragile temperature and pressure sensors monitoring the entire chain. The mechanical iron at the core of the Cummins ISX was still a marvel of engineering. The block, the crankshaft, the connecting rods, and the pistons were stronger than they had ever been. But the engine was being strangled by the systems bolted to the outside of it. In the service bays across America, a new and painful reality set in. Trucks were not being towed in because they had spun a main bearing or dropped a valve. They were being towed in on the hook because a $50 DF level sensor had failed, triggering a software code that shut the engine down to 5 miles per hour. This technological shift devastated the independent service network. In the era of the N14, an independent mechanic with a toolbox and an oil-stained service manual could keep a fleet running. But to diagnose a 2010-era ISX, a shop needed a proprietary laptop, thousands of dollars in software licensing fees, and continuous factory training. The diagnostic tree for a single check engine light could be 40 pages long. Independent repair shops, the bedrock of the American highway system, began to turn away engine work simply because they could not afford the computers required to talk to the machines. This complexity also broke the traditional business model of the independent owner-operator. A driver who owned a single truck could no longer predict their operating costs. A cracked DPF filter or a failed SCR doser could result in a $10,000 repair bill and a week of lost revenue while waiting for parts at an authorized dealership. Mega fleets, massive corporate trucking companies with hundreds of trucks, could absorb the downtime and the warranty claims. The independent driver could not. Cummins, as a corporation, survived the transition. They adapted, engineered their way through the rule book, and continued to sell hundreds of thousands of engines, remaining a dominant financial force in global manufacturing. But the brand's relationship with the American mechanic had been permanently altered. The old trust was based on physical transparency, the idea that if you could see it and hear it, you could fix it. The new reality was a locked black box. The engine still ran, the software updated, the sensors failed, the filters clogged, the tow trucks arrived, the laptops took over. The wrench was replaced by a code reader. The old sound faded. The iron was still strong. The system around it had collapsed. The engine still moved the freight. But the era when a driver could fix a million-mile block on the side of the highway with basic tools was dead. Cummins Inc. did not collapse. Unlike many legendary American industrial names that were broken apart, sold to private equity, or reduced to a mere sticker on a foreign-built product, Cummins adapted. Today, they remain a global manufacturing powerhouse. They mastered the complex world of exhaust gas recirculation, diesel particulate filters, and selective catalytic reduction. Their modern X15 engines pull massive freight across the interstate highway system, and their research facilities are investing heavily in hydrogen fuel cells and battery electric powertrains. The corporate entity survived the regulatory storm, but the specific mechanical empire they built, the era of pure, unadulterated iron and fuel, was entirely dismantled. But American engine culture rarely accepts a regulatory death sentence without a fight. In the years following the 2002 and 2007 emissions mandates, a quiet rebellion took hold in the heavy-duty trucking industry. It was called the glider kit. A glider is a brand-new factory truck, complete with a fresh cab, frame, suspension, and interior, sold legally without an engine or transmission. For independent owner-operators who refused to accept the downtime and repair costs of the new sensor-heavy engines, the glider kit was a lifeline. Mechanics would take a wrecked or retired truck, pull the cast-iron Cummins N14 block, send it to a machine shop for a complete overhaul with new wet sleeves and pistons, and drop it into the brand-new chassis. This was not a fringe hobby. It was a multi-million-dollar loophole. Entire assembly facilities sprang up in the American Midwest dedicated to building glider trucks. A driver could get the comfort of a modern cab with the million-mile reliability of a mechanical fuel system that did not care about NOx sensors or DEF fluid. Eventually, federal regulators closed the glider loophole, forcing even the holdouts into the modern emissions era. But for a decade, the massive demand for remanufactured N14 blocks proved that American fleets had not lost faith in the engine. They had lost faith in the digital system required to keep modern engines running. While the N14 became a prized commodity in commercial freight, its smaller brother, the 5.9-liter 12-valve Cummins, achieved complete immortality in the American garage. Go to any heavy-duty swap meet, rural farm auction, or diesel drag racing event today, and the 12-valve is treated with the exact same reverence as a Ford flathead or a Chevy small block V8. Because of its entirely mechanical Bosch injection pump, the 5.9L has become the ultimate blank canvas for American horsepower. The early 1990s Dodge Rams that originally carried them have often rusted away to nothing. The bodies disintegrated in the salt of Midwestern winters, and the interiors cracked in the sun. But the heavy cast iron blocks survived. Today, a robust aftermarket industry exists entirely to adapt the 12-valve Cummins into other vehicles. Mechanics pull them from junkyard carcasses and bolt them into Ford F-250s, Chevrolet square body pickups, and custom rock crawlers. They are highly sought after because they represent a closed loop. You do not need a computer module to make a 12-valve run. You only need a battery cable to spin the starter, a fuel line, and air. This fierce dedication to preserving older Cummins diesel blocks is not simply nostalgia for a louder, smokier past. The preservation of an N14 or 12-valve is a physical argument about the definition of ownership. In the mechanical era, when a fleet owner or a farmer bought an engine, they owned the iron, and they owned the right to fix it. They could buy a physical service manual, order the replacement parts, and rebuild the machine in their own shop. In the modern era of software-controlled powertrains, ownership has fundamentally changed. A driver may hold the title to the truck, but the manufacturer owns the software that actually allows the engine to generate power. If a proprietary computer code decides an emissions parameter has been violated, the engine will shut down, and the owner is legally and mechanically locked out of the repair process until an authorized laptop is plugged into the dashboard. The old red blocks are hoarded, rebuilt, and kept alive because they are the last heavy-duty machines that answer only to the person holding the wrench. America did not stop needing heavy power. The interstate highway system is still choked with freight. The agricultural combines still harvest the Great Plains. The economy still moves exactly the way Plessy Cummins imagined it would when he drove his experimental diesel truck across the country in 1931. What vanished was the transparency of the machine. The nation traded the raw reliability of heavy iron for the environmental compliance of the microchip. It was a necessary trade for the air we breathe, but it came at the cost of the independent mechanic's independence. Today, the red paint of a vintage Cummins block still commands respect, but it is no longer the sound of the future. It is the sound of a closed chapter in American manufacturing, a time when a driver's greatest asset was the simplicity of the metal turning beneath their feet. Somewhere in the American Midwest, at a quiet salvage yard just off the interstate, a rusted N14 block sits on a wooden pallet. The paint is flaking and the oil pan is dented. It is waiting for a rebuild that may never come, holding inside its heavy cast iron walls the silent memory of 1,000,000 miles, in an era of American power that will never be built again.